Hello everyone. This tutorial we will be reviewing exercise 5.3, 6.1, 6.2 and 6.3. So 4 exercises I will be reviewing in this tutorial. So let's take the first question from exercise 5.3. So in the first question, so this is the question number 3. So we have to find the value for f2 for each of these parts. So let's take the part number A. Right, so we know that f0 is equal to -1, f1 is equal to 2, and for n equals to 1, 2. So we have to find the value for f of n plus 1. Right, so we have f2 equals -1, f3 equals to 5, we have f4 equals to 2, we have f5 equals to 17. Right, so we have basically to find the value for f2, f3, f4 and f5, and we already know the value for f0, f1, and then we sort of just plug the values for 2, 3, 4 and 5 in place of n, and then we get the value for the statement here. All right, let's move on to the next part. Part B, we have f2 equals -4, then we have f3 equals √2, we have f4 equals -4096, we have f5 equals to it's a pretty big value, so you'll definitely need a calculator for that. So 536 870 91. So I already solved it for you guys just to save some time. Let's take part C. Part C is no different, it will be just the same thing. So part C, we have f of 2 equals to 8, f of 3 equals to 176, f4 equals to 92,672, f5, it's a pretty long one, so 25,764, 174 and not done yet, so 848. Okay, all right. So basically what we did is basically taking the 2, 3, 4, 5, plugging it into each function and getting the value for where n is equal to 2. We are calculating the function value. All right, so nothing too fancy here. Let's move on to the next question from this exercise, which is question number 15. So we have to show that f0, f1 plus f1, f2 plus the statement where n is a positive number. Alright, so first of all we will be proving this with the inductive hypothesis. So here we will have the basis step. Alright, so in the basis step we say f to the power right, f0, and then we have f1, then I'll just copy this, f0, f1 plus f1 and then f2, this is equals to 0 dot 1 plus 1 dot 1 equals to 1 square, which is equals to f2. Alright, so that is the basic step. So we take the least element in the domain where n is a positive integer, right? So the least positive integer that we have here for f0, so f0 to the power here. So this is 1, so we take 0 here. Now the next step is of course the inductive step. Alright, so in the inductive step, we will have our inductive hypothesis where we say that assume that this f0 f1, this statement here is true, and then we have to prove that it is true for n plus 1, right? So I can just, instead of writing that, I can just dive into it. So f square 2k plus f 2k and then f 2k plus 1, and then we have plus f 2k plus 1, and then we have f 2k plus 2. So basically we did our inductive hypothesis in which we say that assuming that this is true, we have to prove that it is also true for n plus 1. So I'm just writing out that statement here. So f2k, then we have f2k plus f2k plus 1 plus f2k plus 1 and then f2k plus 2. Alright, so this is basically equal to f2k so here we have f2k, so 2k f2k, then we have f2k plus 2, and then we have f2k plus 1, f2k plus 2. This is equals to f2k plus f2k plus 1, then we have 2k plus 2, and then this is equals to f to the power of 2. So we started with the very basic step here, which is we're taking the smallest element in the domain. We proved that the basic step is true. We move towards the inductive hypothesis step. In the inductive hypothesis step, we assumed that this statement is true, which basically is our inductive hypothesis. And then we sort of prove that it is also true for n plus 1. So therefore, at the end, we proved that this statement holds. So therefore, hence proved. Hence, hence proved by induction. All right. Okay. Let's take another question from this exercise here. So which is question number 27. So we have let S be the set of positive integers defined by a basis step. So we have the proper induction here, and then we have to basically show that if n is belongs to S, where S be the set of positive integers, then this 3n belongs to S and n squared belongs to S. So basically, let's do part A. All right. So we have the basis step. We know that 5 is logically equivalent to 5 mod 10. Inductive step. If n is equivalent to 5 mod 10, then 3n is equals to 3.5, right? Because here n equals to 5 mod 10, so it's 3.5 equals to 15, right? We said that 5 equals to 5 mod 10, right? So we are just replacing this whole thing with 5. N is equals to 5. We put 5 in place of n, so 3.5 is equals to 15, which is logically equivalent to 5 mod 10, and n squared in that case will become 5 square, right? Because we are saying that n equals to 5, so which is basically equals to 25, right? And logically equivalent to 5 mod 10. Mod 10. Okay. Okay, so this is proved. Part B. Show that there exists an integer m logically equivalent to 5 mod 10 that does not belong to S. So we have to find such an integer. For example, one such integer is 35. Doesn't belong to S. The reason why is because 35 is not a multiple of 3 nor a perfect square. Alright, let's move on to the next one. So here we have question number 33. It says define well-formed formula of sets variable representing sets and operators from these sets of operators. Okay. So now if maybe you can use a little smaller font. Yes, this is good. Okay, so if X is a set or a variable representing a set, then X is a well-formed formula. Okay, if X and Y are well-formed formula, then so are X union operator, Y, X intersection operator y and x minus y. Alright, so if x is a set or a variable representing a set, then x is a well-formed formula. If x and y are well-formed formula, then so are x union y, x intersection y, and x minus y. Alright, so this is this is it for the 5.3 exercise. Let's move on to 6.1 now. So it is on page number 416 of your textbook. So basically we have 6 different airlines fly from New York to Denver and 7 fly from Denver to San Francisco. How many different pairs of airlines can you choose on which to book a trip from New York to San Francisco? We are Denver. When you pick an airline for the flight to Denver and an airline for the continuation flight to San Francisco. Right, so basically we had 6 different airlines to fly from New York to Denver, right? So we have 6 different airlines fly from, and then we have 7 different airlines fly from Denver to San Francisco. So basically what we do is 6 multiplied by 7 equals to 42, right? So it's the possibility that we need to basically figure out. Okay. Question number 7. How many different 3-letter initials can people have? All right. So we know there are 26 letters in English alphabet. So we have 26 letters, and we want 3 letter initials, different 3-letter initials. So that'll be 26 to the power of 3 that a people can have. Okay. So question number 13. So how many bit string with length not exceeding n, where n is a positive integer, consist entirely of 1s, not counting the empty string? All right. So we have to find the bit strings with length less than n, where n is some positive integer, consists entirely of ones, not counting the empty string. Right? So the answer is not counting the empty string. So we have n plus 1, and with counting the empty string. Alright, the next one, how many strings are there of lowercase letters of length 4 or less, not counting the empty string? So here we have 475, 255, counting the empty string. Alright, next question. So we have how many positive integers between 100 and 999 including inclusive are divisible by 7? So we have 128 of them are odd numbers. So we have between 100 and 99 we have 450 have the same 3 decimal digit, so we have 111, 222, 333, 444. So we have in total 9, right, including the 999. Then we have are not divisible by 4. that'll be 635 are divisible by 3 or 4, so that'll be 450 are not divisible by either 3 or 4. It will be yes, exactly 450 again. And then we have are divisible by 3 but not by 4, so 225 are divisible by 3 but not by 4. Are divisible by both 3 and 4, they will be less, so there's 35. Okay, alright, let's move on to the next exercise. So we have in this exercise we have question number first, question number 3. This exercise is on page number 426 of the textbook. So we have a drawer contains a dozen brown socks and a dozen black socks, all unmatched. A man takes socks out at random in the dark. How many socks must he take out to be sure that he has at least 2 socks at the same color? Right, so he has a dozen brown socks and a dozen black socks, right? So in total he has 12 plus 12, 24, right? And he basically has to um, make sure that he take out at least 2 socks of the same color. So that will be after 3 tries that he will be able to find out at least 2 socks of the same color. How many socks must he take out to be sure that he has at least 2 black socks? So here we have dozen brown socks, right? So after he has a dozen brown socks, so that'll be 12. 12 plus 2, so that'll be 14. So after this, he will basically have at least 2 black socks after 14. Okay, let's move on to the next one. So undergraduate students at a college belong to one of our 4 groups depending on the year in which they are expected to graduate. Each student must choose one of 21 different majors. How many students are needed to assure that there are 2 students expected to graduate in the same year who have the same major? Alright, so basically we have undergraduate students at a college, and they belong to one of our 4 groups depending on the year in which they are expected to graduate. Each student must choose one of 21 different majors. How many students are needed to assure that there are 2 students expected to graduate in the same year who have the same major? Right? So here we have basically 85 students are needed to assure that there are 85 students are needed to assure that there are 2 students expected to graduate in the same year. Who have the same major. Right? The reason here is because so we have a 4 year 4 groups, right? So and we have 21 different majors. we have 4 groups and 21 different majors, right? So if we say 4 multiplied by 21, this is equals to 84. This basically means that there will be a person graduating from each um, there will be a person expected to graduate in the same year who have the same major, but we want to make sure there are 2 students expected, so therefore we add 1 to it, so it becomes 85. Right, let's move on to the next question. Question number 17. How many numbers must be selected from the set to guarantee that at least one pair of these numbers add up to 7? All right, so so for example, if we have 6 plus 1, it adds up to 7. 5 plus 2, it adds up to 4 plus 3 adds up to 7, right? So there are 1 2 3 4 5 6 and 6, and then there are basically uh 3 such pairs which actually adds up to 7. So this is uh 1 plus 6 7, 5 plus 2 7, 4 plus 3 7. To guarantee at least one pair of these numbers that add up how many. Okay, so basically we have to select at least 4 numbers, right? Because, so for example, 3 pairs, we know that 3 pairs will sure give us the number 7 when they are added together, but we want to show that this is guaranteed that there is at least one pair, so we basically add 3 2 plus 1, which is equals to 4. All right, so sorry, don't mind the background noise. Okay, so we have to construct a sequence of 16 positive integers that has no increasing or decreasing subsequence of 5 terms. So 16, so we have we can just create any sequence, so 4 3 2 that has no increasing or decreasing subsequence of 5 terms. So we have 4 3 2, so it doesn't have to be the 5th term, shouldn't be a decreasing one, right? I cannot put 0, I can put anything other than that, so maybe like 8 7 6 and then 5, and then I should not put 4 because that will be a decreasing sequence. I can put any number, like I can put 12 11 10 9, and then I cannot put 8, I can put maybe 16, and then 15 14 13, right? So that is a 16 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. Yeah, all right, so that is a sequence. Continuing, question number 23. Show that there are at least 6 people in California, population 39 million, with the same 3 initials who were born on the same day of the year but not necessarily in the same year. Assume that everyone has 3 initials. Okay, so now that we know that everyone has at least 3 initials, then we know that how many possibilities are there. Let's show that there are at least 6 people in California, population 39 million with this. Okay, so there are around 6 4 3 2 8 16 possibilities for the 3 initials and a birthday. All right, so by the generalized pigeonhole principle, there are at least, so the population is 39 million, right? So 39, and then there are 6 years in million, and then we divide this number with the possibility, which is this number here, right? So which is basically equals to 7 people who share the same initials and the birthday. Okay, all right, let's move on to the next exercise, which is exercise 6.3 on chapter number 435 of your textbook. So it's about permutation. So how many permutations of set A, B, C, D, E, F, G end with A, right? Right, so we have to find the number of permutations, so that'll be 720 that ends with an A. Okay, right, next one, find the number of 5 permutations of a set with 9 elements. So we have to find the number which has 5 permutations of a set with 9 elements, right? So we have 9 elements, and then we have the 5 permutation, right? So that will be 15,120. Okay, next one. So in how many ways can a set of 5 letters be selected from the English alphabet? Right, so we know that there are 26 letters, and then we want to know the number of ways. So a 5 letter can be selected from that, so it will be 65,780. Okay, next question. So how many permutations of the letter A, B, C, D, E, F, G contains the string B, C, D? Right, so after running some permutation analysis on this, we know it's going to be 120. The string CFGA, so CFGA, all right, so there will be 24 which will contain this. The strings BA and GF together, both of them, 120. The strings ABC and DE, so that'll be 24. And the strings ABC and CDE, that will be 6. The strings CBA and BD, that will be CBA and BED. Okay, so that will be 0 permutations that will have the string CBA and BED. Alright, let's take the last question. So how many ways are there for 4 men and 5 women to stand in a line so that all men stand together? Alright, so there are 4 men and then there are 5 women, and we have to find the number of ways in which all men stand together. So there are 4 men, so it will be 17,280. And then all women stand together, it will be 14,400. All right. So basically that is pretty much it for the review from exercise 5.3, 6.1, 6.2, and 6.3. And I yeah, so that'll be everything for this tutorial, and I'll see you guys in the next tutorial. Thank you guys, and bye now.